My name is John Mazzie. I'm a member of the technical staff at Micron Technology. Today, I'm going to be talking about a small granularity graph neural network training workload and how that relates to the future of storage. The first thing we're going to talk about is why do we care about storage for training? Well, models are getting much larger. Storage must be used in some way for these large data models. As an example, we have a couple of data models here. One is the data set we're actually going to talk about, the specific workload we're going to analyze later in the presentation, which is the Illinois graph benchmark data set. It's about 2.3 terabytes on disk. And as another example of a larger inferencing model, we have the Meta Llama 4 Maverick. It's about 800 gigabytes on disk, and I believe there's a larger one that is not publicly available yet that is going to also be much bigger than that. One of the ways you can sort of get around this is you could always spend more money on GPUs for more memory, though just buying GPUs for memory isn't necessarily going to give you the best bang for your buck. And then also, you're limited to how many GPUs or DIMMs you can actually put in a single system if you were doing that. So you need some type of expanded storage, whether it's disaggregated or things like that. I'm briefly going to go over graph neural networks and the basic training operations, and then how that connects to how storage can help us. This is just a basic example of a graph that you use for training. It's made up of nodes and edges, where the edges are essentially just the relationships between the nodes. Node features stored in N by D matrices, which is basically the number of nodes and the dimensions of the features. Typically, these features for a node can be between 512 bytes and 4K. They can be larger, they can be smaller, depends on the graph. For large graphs, data can reach several tens of terabytes, and this can be very challenging with limited memory of a GPU and even some system memory. I'm going to quickly go through the GNN training process. We're going to talk about the process we're going to use in this workload is mini batching. So the training is done on a subgraph, which is sampled and then loaded into GPU memory. The batch size is chosen to prevent GPU memory overflow, and this enables more parallelism as many batches can be assigned to different GPUs. Studies have demonstrated that this technique can lead to faster convergence and better optimization. And then we have graph sampling, which is how we generate these subgraphs. And there's different methods. One is GraphSage, and it has the concept of neighborhood sampling. So this reduces computation and memory footprint by randomly selecting a fixed number of neighborhood nodes. So it uses a random distribution. You give it the number of layers, number of hops, and the total number of nodes, and it will randomly generate a subgraph for you to use for sampling. Feature aggregation, which really this is the section where the storage is going to help out. The features of the subgraph are gathered for small graphs where node feature data can fit in CPU memory. Sampling's done. The selected data is then transferred to GPU memory where training is performed. If a graph is too large for system memory, the data is going to be stored on storage devices. The sampling will occur, the sample data will be buffered to CPU memory, and then transferred to GPU memory for training. And this is the standard way of doing it, but we're going to be talking about another method to improve the performance of this and why faster storage is ultimately necessary, not to jump the gun. The data transfer, just transferring the data from either memory, storage, or system memory to GPU memory to do the training. And then model training is magic. I do not actually know how it all works. So the project we've worked with and presented data on in the past, we've worked with NVIDIA to use its GIDS, GPU-initiated direct storage. The current state of the art is memory map storage, where you essentially have the data on the storage device treated as memory. And so when you try to retrieve the model from system memory, if there's a miss, then you need to go grab it from storage, but there's a lot of overhead with that within the CPU. With the system memory misses and then retrieving from storage and then buffering it back to the GPU. With GIDS, this actually utilizes the GPU to initiate and do the transfers. So completely bypassing the CPU complex for I/O transfers. This leverages the high parallelism of the GPU, which gives you much better performance because it already knows it's going directly to storage. It's completely bypassing system memory. I'm now going to talk in more detail about the data set we use to do these performance. The Illinois Graph Benchmark data set. It's an open source data set. It's on GitHub. It was generated because there's a lack of large-scale publicly available data sets. Most very large data sets are proprietary to companies, and obviously they don't want to share that data because they're using it to generate revenue. Another issue is public data sets, even if they are large, sometimes have very limited labeled data. The Illinois Graph Benchmark dataset has a few different types of graphs. They have two different types, homogeneous and heterogeneous, where the homogeneous graphs are a single node type and a single edge type. So think of a simple social network graph where the node is just a person and the edge is just the relationship between these people. And the heterogeneous graph, which is the one we will use for our evaluation, has multiple different types of nodes and edges. This data set has more than 220 million labeled nodes, which is more than 40% of the data in the heterogeneous graph. The embedding dimensions for the homogeneous graph range from 128 to 1024. For the heterogeneous graph that we're using, the dimensions are 1024. And then you get about 570 million nodes with 5.8 billion edges on that, with that data set. And the data set, as you can see, is essentially the relationships between publications with authors, institutes, field of study. This is our initial testing where we showed how does GIDS improve, and these are generally 4K transfers because the featured nodes are about 4K. So we compared the classic memory map where data's in storage, but we use the CPU, try to access it with system memory, get a miss, have to pull the data in. And you can see where feature aggregation drastically increases if we completely bypass that and go directly to storage when we know that's generally where the data's at. We get about 2 orders of magnitude improvement. So from 1100 seconds for the feature aggregation down to about 20 seconds with just one Gen 5 NVMe. And with up to 4, we can saturate 1. This was tested with an A100, I believe. And yes, an A100, I think. You can get it down to 5.89 seconds. So you get huge improvements by going to this GPU-initiated direct storage, and then you get your linear improvements as you can saturate the bus with multiple devices. We also traced this workload, and it's from a storage perspective, this was about 99% random read and 1% random write. And this is because the way GIDS works is it has a cache that is built into the GPU memory, so it pulls the data in that it is training, and it will do almost all of the writes there and only really write back to the storage when it needs to update the model. And we read the data from many nodes in order to train and update a single node. This is an example of the QDEPs we see with this workload. In classic data center, we always considered high QDEP to be in the hundreds of transactions to a disk. But with GIDS, we could see between 8 and 10,000 on average, which is a lot, but that's because there are a lot of cores on these GPUs. And they are trying to overcome the latency, the higher latency of the NVMe device by having tons of transactions, so when your transaction comes back, you can just immediately start working on it. So you're trying to mask the high latency with these higher, with having a lot of transactions in process. This is the same data, just shown as a histogram over the entire test period. So you can see that most of the time the Q depth is between 6,000 and 12,000. This is a much higher Q depth than expected when everyone was designing NVMe devices originally. And then there's like questions, what can we do in the future? What optimizations can we make to handle these higher number of transactions? Would this workload benefit from more Q pairs? It's hard to tell. I am going to now talk about how SSDs handle smaller than 4K transaction workloads currently. So typically, if you're doing 4K reads, you do the read, the storage controller goes to the NAND, reads 4K of data that you request, brings it back, gives it to the host. If you do smaller than that, let's say 512 bytes, which matches an LBA size, you do your 512 byte read, the controller then goes to the NAND, reads 4K back, gives you 512 bytes back. So you're reading more data than you're actually requesting. And you can do caching and optimization to this, but since this workload is mostly random, read ahead and caching strategies don't really help that much in this case because data is unlikely to come from the same page within the SSD. And for this workload, the low percentage of writes really doesn't concern us very much, but for a different workload that's not graph neural network training, this could matter as there may be more writing up at these smaller transactions, or there will be more writing up at these smaller transactions. If you have many writes, you're going to have a lot more write amplification on your disk. And then I kind of alluded to this, but there's controller limitations. Since they're designed to do 4K transactions, that's generally your top IOPS number. Most of the time, your controller is not going to do more IOPS just because you do a smaller transaction to it. So going down to 512 byte transactions, your Gen 5 controller is still going to do about 3 million transactions a second, not 8 times 3 is 24? Yes. We did a proof of concept with some synthetic testing. This was using our Gen 5 device in a Gen 4 system where we test the IOPS for using lower transactions. So we used NVIDIA Blockbench, which is a synthetic benchmark that's included in NVIDIA's BAM, Big Accelerator Memory, which is the underlying system that GIDS is built on. You could do the same test with FIO, but since we wanted to use the same architecture that we were using for GIDS, we chose to use NVIDIA Blockbench. But essentially what we show is if you had a faster drive in a smaller or in an older PCI generation, you could still benefit from the higher IOPS given by the newer controller because you can do the higher IOPS, you're not limited by the bus bandwidth at that point. But they would not give you more 4K IOPS, but smaller than that, 2048 down to 512, you would see the improvement. We did also do a modified version of the GNN training test. We took the heterogeneous data set, and then we modified those 4K features into 512 byte features. So this is so we could do the same training workload with these smaller transactions. And the test system we did this one was a PCIe Gen 4 system with the NVIDIA A100 and used our PCIe Gen 5 drives. So there's a couple different tests we're going to talk about. One is going to be the training using BAM cache and GIDS, which is doing 4K reads, just like the previous testing, except it only now needs 512 bytes of the data. And then also using the same thing with 512 byte reads, so only asking for the data it actually needs. And then we're doing this over various cache sizes within BAM. So quickly from this graph, this gray chart, or the gray line at the top is the results from the 4K workloads, and the magenta line is the results from the 512 byte workloads. And you can see generally switching from the 4K reads to the 512 reads with the faster drive in the older generation system, we do get 1.8 improvement in performance. So on the left, we have the feature aggregation time, which is the y-axis. And then across the bottom, we have the cache size. And we can see performance improves as your cache size goes up. There are a couple outliers, but in reality, we expect those to follow the 4K graph. And what you can see here is, okay, having a higher cache obviously gives you more performance. But what happens is, if you use too much of your GPU memory, then you also don't leave as much memory for the actual training that's being done with the rest of the memory on the GPU. Let's see. And this is the same test, but with 4 NVMe devices instead of 1. So you don't really see a 2x improvement there with the improved. But if you had a single device that could do, 4 to 8 times more 512-byte transactions on a disk, this would be ideal for this situation. So basically, the goal would be to design a system, or an SSD, where you could do line rate 512-byte random read transactions for a specific workload. And now I'm going to talk about the ecosystem enablement that we need to do. So because the GPU can drive so much more I/O to the SSDs, with the benefit of skipping the CPU, it seems like we need a drive that can do more transactions, even more than just our Gen 5 and even potentially Gen 6 and Gen 7, from a 4K perspective at least. And here's the essentially evolution of this GPU direct storage. We have NVIDIA GDS, which the data flows to the GPU, but the control plane is the CPU and DRAM. We have big accelerator memory, or BaM, where the data control path is actually on the GPU, and then data flows directly from storage to the GPU, completely bypassing the CPU. And NVIDIA is currently working on SCADA, which they've talked about at GTC, and it's built on BaM, but it also adds this client-server architecture, so you can disaggregate the storage from your actual client compute and training. But new storage is required to avoid these system bottlenecks. We have done some preliminary testing with SCADA, and with our Gen 6 drives, we actually were able to reach linear scaling from 1 to 20 devices with an H100, and this essentially maxed out the PCIe bandwidth on the Gen 6 system that we had from H3. Now, in the future, NVIDIA has organized a group called Storage Next, and it's a group of industry participants that look to the future of storage for AI workloads. With the advent of GPU-initiated I/O and the large number of small transactions, but also large data sets and models, using storage can't be avoided. Current storage isn't designed for much small granularity accesses, and to reduce the number necessary to reach the transactions, a new paradigm is required. So, potentially looking at any and all possibilities. But that's all I have. Are there any questions? Yes. Mm-hmm.
Do you still think that is it still valid to drive AI storage requirement from
That I am unsure. So this is more about like from the storage thing. So and I'm not sure what LLM, are you talking about inferencing specifically or just the training of an LLM model? Both, yeah. From an inferencing standpoint, so the question was, do I see this GNN requirement versus LLM? I think things are just different between the workloads. This is the workload we had access to test this system, which is why we chose it. But I'm not really sure from an industry perspective. LLMs are obviously important. I think inferencing is a different workload than this from the storage perspective, and that's going to take more advantage of, a lot of people have talked about KV cache, and that's going to be a different workload than this training workload. And I'm not as familiar with the LLM trainings as I am with the GNN, so I can't really answer the other question. Yeah. Mm-hmm.
For the CPU results, did you use SPDK or did you use the kernel driver?
So the question was, did I use SPDK or the kernel driver for the CPU results? And for this one, it was the kernel driver. It was not, no, we did not use SPDK, which definitely has optimizations and can drive a lot more I/O to devices with more limited CPU usage.
Did you use FIO and IO ring?
I'm sorry, repeat that?
Did you use FIO?
I have used FIO and IOU ring to run similar to the synthetic testing, and you can do that when I'm just testing the IO throughput, but then I'm also not actually doing the training. Whereas the other workload where I'm doing the GIDS training is actually doing GNN training on the data set on top of the IO, not just the synthetic transactions.
Which libraries you use? Is it using libaio or IOU ring library?
I've done both with libaio and IOU ring, yes. Any other questions? Yes.
Your GIS result should be you show the graph that there are some improvements when you use your SSD 955.
This chart?
Is there any some specific optimization in the SSD side?
No, this was more of a proof of concept that said if we could make a SSD that did more of the smaller transaction IOPs, could you take advantage of it even on a current gen system? So we tested a Gen 5 drive, which could do double the IOPs of a Gen 4 drive on a Gen 4 system to purposely limit it at 4K, and then did the smaller transactions to show that, yes, in this case, it would improve if we had a Gen 4 drive that could do, let's say, double or quadruple the number of transactions at 512 than 4K. So it was more of a proof of concept rather than just saying, yes, this drive is really great for this workload. Okay. Mm-hmm.
Can you explain the spike here?
No. So when we ran the testing, these two tests had an outlier. And I suspect it was because we were currently using experimental code at the time. We had modified the data set. So there may have just been an issue with these specific test runs, but we didn't have time to actually go in and figure out exactly what went wrong with these two tests. But in reality, they should match the 4K test because the data sets are the same, but at least the slope should be the same. And even in the 4-drive test, you see a slight spike at 16 gigs. So I'm suspicious, but I don't know exactly why those were up. Yep. Is there anything else? Okay.